Section 2.4, Product and Quotient Rules. Our objectives are 1. Find derivatives using the product and quotient rules, and 2. Apply and interpret these concepts, including average cost and average revenue. In this section, we'll expand the functions we can differentiate by learning how to find derivatives of products and quotients of functions. The product rule is the derivative of the product of two functions f and g is the derivative of f times g plus f times the derivative of g, where f and g are differentiable functions of x. I usually think about it as the derivative of the first times the second plus the first times the derivative of the second. Let's do some examples. Find the derivatives of the following functions. H of x is 2x squared minus 1 times x cubed plus 3. Now, we can go ahead and multiply these quantities out and then find the derivative. Let's just do that so we can see what we get. So we would have, first, rewrite the function h is 2x to the fifth plus 6x squared minus x cubed minus 3. Okay. Oh, now we can find the derivative. 10x to the fourth plus 12x minus 3x squared. Okay, let's go ahead and find the derivative of h using the product rule, and then we'll revisit our work here. So let's let the first quantity be the function f, and the second quantity be the function g. Then f prime would be 4x, and g prime would be 3x squared. So then we can just plug in our pieces. The derivative of h is the derivative of the first times the second plus the first times the derivative of the second. Now, in my open math, for the product and quotient rules both, it is perfectly acceptable for you to enter in your solutions in this fashion. You are not required to multiply this all out and get it together. However, we're going to do it here so you can see how it works. So if I multiply this through, I'm going to get 4x to the fourth plus 12 plus 6x to the fourth minus 3x squared. Combine like terms. And we get exactly the same answer, as we should. Let's go ahead and do another example. I think the key to success here is just identify the pieces. So if this is my f and this is my g, I want to remember that g could be written x to the 1/2 plus 1. So the derivative of f is 3x squared, and the derivative of g is 1/2 x to the negative 1/2. So now we have all the pieces we need for our derivative. H prime is the derivative of the first times the second plus the first times the derivative of the second. And for our purposes, this is sufficient. Let's do one more. If we let f is e to the t, remember the derivative of e to the t is also e to the t. And if g is the natural log of t, then the derivative is 1 over t. So our h prime would be the derivative of the first times the second plus the first times the derivative of the second. And we are done. Let's take a look at the quotient rule. The derivative of a quotient of two functions is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. I specifically stated this in terms of numerator and denominator to help you remember which they are. You also might want to think about it as the derivative of the top times the bottom plus the top times the derivative of the bottom all over the bottom squared. Let's do some examples. So if this is my f and this is my g, then the derivative of the top is 2x, the derivative of the bottom is 2, and our derivative of this function h is the derivative of the top times the bottom minus the top times the derivative of the bottom. So, all right, 2x squared will work there. We don't need all the parentheses. All over the bottom squared. Again, in my open math, for our purposes, entering your solution like this is just fine. You do not need to multiply everything through and simplify as much as possible. Now, you may want to evaluate a derivative at a particular value, but frankly, I think in this form, it is just as efficient to sub your values into these places as to have it all multiplied out and then sub in. Let's do one more. So here, if there's my numerator, my denominator, and the derivative of the numerator and the derivative of the denominator. So the derivative of our original function h is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. I know that if you get in some practice right away, you're going to master this pretty quickly. Let's take a business perspective. The average cost, or AC, for Q items is the total cost divided by the number of items, Q. So the average cost at Q is the total cost at Q divided by Q. You can also talk about average fixed cost, which would be taking the fixed cost divided by the number of items, or average variable cost, which would be taking the total variable costs at that number of items divided by the number of items. Average revenue for Q items is the total revenue divided by the number of items. So total revenue divided by the number of items. We already know that we can find average rates of change by finding the slopes of secant lines. Average cost, average revenues, marginal change, and marginal revenue are all rates of change, and we can find them with slopes too. For example, the average cost at Q is the slope of the diagonal line from the origin to Q at total cost of Q. The average revenue of Q is the slope of the diagonal line from the origin to Q, total revenue evaluated at Q. Let's work an example. Find the following given the cost function in thousands of dollars for producing X thousand widgets. Our cost function is 17 plus X minus 5 thousandths X squared. So what are our fixed costs? That would be the cost at producing 0 items. So the cost of 0 items would be 17, but this function is given in thousands of dollars. So that would mean our total fixed costs are $17,000. Find the average cost when 5,000 widgets are produced. So the average cost would be the total cost divided by the number of items. So we want to evaluate the cost divided by the number of items. And that would give us the average cost function. So we can also go ahead and simplify. That would be 17 over x plus 1 x over x minus 5 thousandths x. And we could even write that in exponential notation. So we've simplified the function. Now to evaluate the average cost at 5,000 widgets, since we're talking about a function given to us for thousands of widgets, then we would sub in a value of 5 into the average cost function. So the average cost at 5,000 units would be this. Now I looked at this function and I said this would be more efficient to calculate. So we're going to do that first. So we get a value of 4.375. I'm going to round to the nearest penny. So the average cost at 5,000 was $4.38 each. And we estimated that from $4.37.50. You're going to want to make sure throughout the course, when you're doing the applications on MyOpenMath, make sure you look for the units that they want you to give the answer in. Let's find the average cost when 10,000 widgets are produced. So again, we want to enter at 10. So that's what we're going to enter. And now we're at about $2.65 each. So the reason our price is coming out price per unit is that it's this many thousands of dollars divided by X thousand units. The thousands divide out. So we're still coming up with $2.65 per item. Find the marginal cost. Find the marginal average cost when 5,000 widgets are produced. Now that means the marginal average cost is the derivative of the average cost. And that is why I went ahead and translated the average cost function into exponential notation. Now I'm set up to take the derivative. Derivative of 1 is 0. So here is our derivative of the average cost. So when we want to evaluate that at 5,000 units, this is what I come up with. Well, what the heck does that mean? Remember that marginal average cost would be, we're talking about the rate of change of the average cost at 5,000 units. So what this is telling me is at 5,000 units or items, the average cost per item is decreasing by about 17.5 cents for each additional X, but X is 1,000 items. We'll do more work with business applications throughout the course.